Well, I'd like to plot this like I did for the square wave example, but it isn't obvious to me at all what this looks like. I could just type the expression into the computer and have it plotted, but I'd rather get some more understanding here. Now, I want to show you a cute little trick. This is really important thing to appreciate, and it has to do with this little part of it right here. So a little math. So I want you to note that I have a term that looks like 1 minus e to the minus j theta. Suppose I factor out what we call half the phase. So I'm dividing this phase up here by 2, and I pull out that factor. Well, I hope you agree that this and this are the same thing. Okay? That cancels that, and now I get my phase back to where it was. Well, that's very exciting, because if I divide this by 2j, multiply by 2j, what's that? Well, that turns out to be Euler's formula for a sine wave. And so after all is said and done, this term here is equal to that. And so there's a sine buried in there times a complex exponential, a phase term. So that means using that result, I can plug that in, simplify the expression, and here's what I get for a final answer for the Fourier coefficient of a periodic pulse train. It has a sine, what we call a sine x over x behavior, known as a function of k here. You get sine over the argument times the same thing. So if I take this and multiply by delta and divide by t, and I'll do the same thing up here, delta over t, then I have something that looks like sine x over x. And this has got a name. This is called the sinc function. And I need to know what a sinc function looks like. And here's the plot of a sinc function. Very important for us. It turns out it's going to reoccur in this course a lot. So, sinc function, the reason it's going through 0, of course, is because of the sinc. Its amplitude is dying like 1 over x. At the origin, that's the interesting part, notice you get 0 over 0, and you have to use L'Hopital's rule to figure out, and you'll quickly discover that it's equal to 1. So this is a plot of our sinc function. 1 at the origin, and then looks like a sinusoid with the amplitude going down like 1 over x. Okay. So that means we can plot now our spectrum for a periodic pulse sequence. Again, I'm plotting this in terms of harmonic number, and frequency is k over t. So the t is understood. And this plot applies for this special case where the pulse width is 1/5 of the period. Just a special case to plot it. And now we see that all the Fourier coefficients are non-zero, except in the case where they are harmonically related to 1 over delta over t. And that's the way, because of the sinc behavior, right? It goes to 0 at some places. Okay, so there's our sinc function, except we're plotting the magnitude, so those negative parts in the previous slide go above the axis, and we have to change the phase. But the point is, again, the spectrum of periodic pulses consists of a lot of harmonic terms whose amplitudes are generally decaying, but now they ripple up and down depending on what the values are, but generally they're going down. The phase is interesting. It turns out it looks like the phase should be a linear function. Remember, the phase is just that argument, what is multiplying j, and it looks like it's linearly decreasing. It's got a negative slope, and it looks like it should do that forever. And why do I have this funny plot where it pops, it looks like it's doing what it's supposed to, then it pops up and does it again? And that has to do with a complication of the sinc function. In this area where it goes negative, that adds a phase of pi to the in the phase term, right? Because you can't, magnitude cannot go negative, so that pops into the phase. Well, the next value on this straight line was going to be minus pi. I add a phase of pi because it's going negative, and it pops it back up. So that's what all these have to do with, is returning to the original values because of the phase. Sort of the phase of the sinc coming into play. Has a kind of a subtle phase. It may be real valued, but it still has a phase. Negative numbers have a phase of pi, or minus pi, depending on how you want to think about it. Okay, so let's think about this now. We have a signal that's in both the time domain and the frequency domain. I can express it as a superposition of rather complex exponentials. Can I really do that? Are they really equal to each other? And so I need to explore that in more detail. And what I'm going to do is look at what's called a finite approximation of this term and see what happens as I let k get big. So if we start with our square wave and look at it for some value of k, well, this finite sum shouldn't look like a square wave. But as I take more and more and more and more terms in, it had better become the square wave, or I can't write this equality is just wrong. Well, let's see what happens. And this gets interesting. So if you only go out to the k equals 1 term, which is the first harmonic, you see that you get the sine wave like you should. And it kind of looks like a square wave, but it's not, certainly not equal to it. As k gets big, I went out to the 49th term here, you see it's becoming closer and closer to the square waves. Really very interesting. You should plot this for yourself sometime. It's really quite exciting how it works. However, Josiah Gibbs, an American mathematical physicist, pointed out something. He noticed, see these little bumps up here? And it may look like they're diminishing. The ripples inside here definitely are getting smaller, but those little bumps, which he called ears, they're known as Gibbs ears, don't go away. And it turns out they will always be there, and they get closer and closer to the point of discontinuity. It turns out the discontinuities are a problem. Well, let's think about this. If we start with a discontinuous signal, like a square wave, well, complex exponentials are all continuous. How can a sum of continuous things add up to be a discontinuous thing? How can this be true? And so we got to call into question the fact that this may not work right. Does the Fourier series really work? Well, it turns out when Fourier presented his work on the theory of heat to the French Academy of Sciences, his work was examined by 3 mathematicians, Laplace, Legendre, and Lagrange, 3 mathematicians you may have heard of. And they awarded him the prize for the best piece of work, but they really called into question what happens when S is discontinuous. It seemed like it worked, like I showed you, but there's these little points, the Gibbs ears, that things don't quite work right. How do you justify that? Well, we have to go off and do a little bit of mathematics. It is pretty easy. So it's been shown that